So thanks very much for the invitation to be here today to give you a taste of the kind of work that is ongoing in my research laboratory. And the title is, of course, Understanding the Songfly Owls, emphasis on the understanding. This is a problem that is not, does not have a tight lid on all those answers, but we have now, over the past couple of years, a good idea of what is going on. So I thought it might be helpful to actually tie this in somehow to actually the ethos of Lehigh itself, which I thought was pretty cool when I first came here. So Lehigh's motto actually is the first couple words of the first aphorism in Francis Bacon's Novum Organum, which was the big work that initiated the scientific method approach. So instead of it being an a priori kind of deduction-based reasoning to get to truth, this uses observation as an avenue to establish certainty and then progress so on and so forth, as you know now in the scientific method. So the title, Novum Organum, translates to new instrument, and what's neat is as an engineering principle, we're always observing nature and trying to get a bit smart about what it's doing. And so I thought it was neat coming here that I already had this biologically inspired inspiration for engineering built into the model itself. So the idea isn't simply to take nature, so you can have, say we take a bird that flies well, we make another bird, we haven't really learned anything except for how to make a bird, right? So the idea of biologically inspired engineering is saying, well, we observe some really cool stuff. Can we now understand the physics and then apply that to something that's, say, similar to a bird, or to airplanes, or to underwater vehicles, things that are outside of the exact element that the inspiration came from. And that's the big push there, philosophically. I really like this tie into the natural philosophy that we have at Lehigh. And I don't know if you've been over to the library and looked at some of the rare books. They have this so-called elephant folio, which is this huge book. You see them with the birds on it. You look straight in as you go into Lindemann. The reason why it's so big is because all of the birds in there are drawn life size. And the way this was created is that John Audubon had these etchings made, which were then printed and then watercolored by the best artists at the time by hand. So each of these is a unique work of art. And I've gone and inspected these for fun. And it turns out that all of the features I talk about in owls that make them silent, even the small scale ones, are captured in detail in these etchings. So it's pretty cool to see firsthand. And Lehigh is one of the 120 surviving copies, the full copy, so it's in 4 volumes. And so, in the nature of Francis Bacon, I thought we'd start with some observations about why owls are, well, what owls do and what we can glean from what they have in their person. So here's a great gray owl, kind of very emblematic type of bird. And you'll notice it has this facial disc, which everyone kind of recognizes being familiar to owls. And I have all of these Lindemann slides actually covered in. These all come from the birds of America. This looks like it's centered around the eye, but in fact it's the disc centers like a handcuff behind an ear, channeling sound into the ear, which gives it a bit keener sense of hearing. And what's interesting about owls is that their ears are asymmetrically positioned as well as sized. And so they can hear, with that asymmetry, they can hear a precise point in space. So we have our great gray owl here, who hears a rustling, say, under the snow. And once it identifies as being something more than just, say, leaves blowing in the wind, identifies as prey, will end up doing this kind of this head bobbing, which pinpoints the point in space he's looking at. So he's looking and hearing in the same direction. The visual and auditory senses are integrated in the owl in a very unique way. So once the owl takes off, what it's going to do is it's going to be looking at a certain point in space. But what it's actually doing is hearing and seeing at the same point. So if it has to go on obstacles like this, it's actually flying in very familiar territories. It doesn't run through a tree. It stays very close to places where it's familiar. So in this way, it's looking and hearing in a certain direction, whereas it knows to fly a certain way. So it's the same great gray owl. jumps off his perch, and because this is a delay, we know that we have to talk about glide paths somehow, right? So 26 degrees plus or minus 4. And the key thing is to maintain this stealth until you're about 1 meter from the target. At that point, you can be noising. It's too late for them to react properly to get away. So even through the snow, it can hear this. It doesn't have to have visual contact because it's actually hearing the point in space. So here it is. The BBC did a nice job of showing this X-ray of the snow. And my favorite part, the first time I gave this, showed this video, is that my supervisor at the time said, "Oh, well, he looked like he was successful, right?" So how many shots it took for the BBC to get that? Who knows? So we're engineers, right? So someone says silent flight, okay, whatever. What does silent really mean? Let's have some numbers, let's have some data that go with it. So to hunt an acoustic stealth, of course, the owl can't be alerting its prey. It means suppressing the noise it makes as it flies through the air to below the threshold of hearing within this frequency bandwidth, so 2 kilohertz and above. It also can't be making noise that interferes with its ability to target acoustically. So it can be making noise within its peripheral hearing or sensitive hearing range, 3 to 6 kilohertz. And so acoustic stealth means for owls, it's getting rid of the noise it's making by flying through the air that would interfere with its hearing or alert its presence, which means suppressing the threshold of hearing, the noise level to the threshold of hearing or below for 2 to 6 kilohertz and above into ultrasound. So if we look at a log plot of where we hear, so here's a light gray, which is our hearing range from 20 hertz to 20 kilohertz, which I can't do anymore. That's for newborns. But the peak range is this 2 to 4 kilohertz range. That's where we're most sensitive. So peak sensitivity for owl prey is in the green. The peak owl hearing, the squeaks and leaves that kind of it's evolved to pick up on, is in the cyan. And this critical frequency range for silent flight is in the red. So why do I even bother putting this here? Well, the critical frequency range for silent flight for owls overlaps with our critical hearing range. So at least on the scale of the owl, if we understand how it's making things quieter, we could adapt that readily to engineering technologies. Or we could understand it and apply it to other things like energy and aviation. So at larger scales.
The bird's challenge.
So
to fly over a series of super-sensitive microphones.
What is it like to actually hear this? It's really
Go. Yeah. How's yours? Smoke.
And now, it's Kenz's turn.
No, nothing at all. Absolutely quiet.
It's amazing.
But what have the microphones picked up? The decibel waveforms showed the sound being generated by the birds in flight. Each spike is an individual wing beat. But with the barn owl, there's almost nothing.
Okay, so that's fun and good for mom and dad, right? But what do we as engineers take away from that video? Well, one is that owls actually are quiet, which is pretty cool. When I started this project a number of years ago, I was quite uncertain that actually they're as quiet as I said they were. Other one is, well, if we did a careful experiment, this isn't a very good experiment to conduct, right? So the owl has a lower wing loading, which means it can flap fewer times over a certain distance, whereas the pigeon has to hold more of its weight, and so does the raptor. They also have them positioned at different points, right? So they had to carry their weight as they go over these microphones. So if you had to design an experiment, this is not the one to do, right? This is the exercise in bad experimentation, but it proves the point that they were trying to make. So I put that as a caveat for watching this video, but actually it's the most scientific one I've seen in a while. So what is it about owls that make them different from other birds in a way that would enable their sonic flight? That's the key question now. The turns out this is an old problem. So the first published account was by Lieutenant Commander Graham in 1934, who showed that these three features are unique to owl species you don't see on other bird species. And they could have some influence on the noise generation aerodynamically. So the first is this fine velvety down material. It's like the texture of velvet, kind of like the hair on the back of your knuckles. It's only about 1 millimeter thick, and is located only on the upper surface of the wing. So I brought a couple of my feathers here. Well, try to take one and pass it around. And probably what would be best is to take the back of your finger and rub along the bottom of the feather. That's the pressure side. And this down material is on the upper side. You can kind of feel the difference there. So it's pretty cool texturally, the difference between the two. And what's unique about this is that it's only 1 millimeter thick, and if it's only doing anything acoustically, it behaves very different than other kind of sound absorbers. So what we did is we took that feather and put it under a microscope, and what we were expecting was something like blades of grass, where it kind of grows out of the ground and they're cut clean off, and that's it. Turns out it has a much different structure than that, and that's what we'll talk about later on as being a mechanism for suppressing noise in a unique way. So Reynolds numbers for those interested. But the structure of this, just like blades of grass, these barbs, the barbels come up off the wing surface, but then have smaller barbs on the tips, which then interlock with each other, the ones next to them, and form this upper kind of canopy layer. So it's like a forest. You have the tree trunks, and you have the canopy that kind of that interlocks it together. And this interlocking porous canopy is the key new finding that we've been playing with for about a year or two. So moving on to other features, there's a leading edge comb, which actually you can see on the Audubon books, which is pretty cool. So these are stiff, evenly spaced fibers along the leading edge, which act as vortex generators to kind of keep the flow attached on the upper surface of the flow. So the spacing of these, the viscous dimensionalization, agrees with experiments for optimal drag reduction at low incidence. But because they're at large incidence, what they think is going on is it's controlling separation and stall. So there were experiments back in the 70s where they took Florida barred owls and trimmed off bits of their wing and saw that they're louder, as well as they couldn't fly anymore. So it was a coupled aerodynamic aeroacoustic problem, but some other measurements done a year later, just leading serrations indicate that you can get noise reductions there as well. So there's a possibility there, but that's not what we've been focusing on. What we've really been focusing on is the trailing edge and its fringe. So you probably see on the back of that feather, it's not a very well-defined edge you have on there. I can actually use the wing. Probably the best thing to show you this. So the feather forms one part of it, right? The other part is actual, how does it integrate with the wing? So the fringe is this bottom part here. So on an airplane, you'd have this very hard aluminum edge that's very well defined. On the owl, it's this kind of fuzzy, nondescript edge put together by a number of feathers. You can take it out of the bag if you want, but be very careful. And so why am I focusing on the trailing edge? Everything that passes through the air creates a boundary layer, and that boundary layer interacts with the back edge to create noise. And what happens on the owl wing is that these streams on the upper and lower surface of the wing come together gradually instead of all at once, which happens on ordinary wings. And so the trailing edge noise mechanism is prevalent for anything that goes through the air. And so to be functionally silent, the edge noise has to be addressed in a unique way by the owl. So here's a future of sonic aircraft. You take all those three things I mentioned, and you throw them on a plane, and voila, you have a sonic aircraft, right? Probably not. And I'd like to point out, this is for Top Gear fans, this is Richard Hammond, who has a show in the UK called Miracles of Nature. We did the Owl special at one point in time. So I laugh at this because it seems near impossible, right? There are obviously trade-offs here. If you have something that may be quieter, it could ruin your performance aerodynamically. And so the idea would be, well, we can have it quiet for only certain parts of the flight pattern. So if you have, we don't care about noise really when they're at cruise, but when we're landing, we certainly want it to be quiet to not affect neighborhoods nearby the airports. And so this is something of a design challenge to how do you incorporate these things in a useful way that can be deployed and retracted. But at the present time, the research level is really to see what the trade-offs are between acoustic stealth and the aerodynamic performance when you have these novel owl features. So I mentioned a little bit about trailing edge noise as a mechanism. So everything passing through the air, every solid body makes noise. And it's from the generation of turbulence in the ventulator that hits the back edge and scatters the sound. So the back edge is an amplifier for noise. And so you have the flaps up, you have the landing gear up, and your throttle back. All that's left is this noise from the trailing edge. That's what you hear swooshing overhead. So compared to rigid wings of commercial aircraft, owl trailing edge, as you kind of felt already, is compliant and porous. So it's a gradual communication of the upper and lower streams. And so the research goal is we look at the acoustic scaling. So this acoustic power of the large pi, it's just pressure times velocity of the noise far away from the edge. And this frequency-dependent function here is characterized by this large drop in noise level beyond 2 kilohertz, which we talked about before. And so what I do in my research group is say, well, we have this general idea of what's happening. How can we then boil this down into a model that we can solve and get some idea of how the parameters play and compare that noise level to, say, an ordinary wing. So again, do a really hardcore computation that would take you months to run. This doesn't have elasticity in the edge either. This is what it would look like. So these guys at Richard Sandberg at Southampton is a world expert in DNS, direct numerical simulation, and he can get these contours here of the turbulent flow being developed, then scattering off the back edge, and then you see the sound field kind of emanating from the turbulent edge, the edge as well as the turbulent region. So that's one end of the spectrum. The other end of the spectrum is, well, we boil down to a turbulent source. The main noise generation happens near the edge, and so what we're modeling is turbulence makes a noise, the energy goes into an elastic wave into the edge, and the rest of the energy is scattered and amplified as sound, which you then hear as a listen in the far field. So as a math problem, go at it. I wouldn't advise it. So what we end up doing is a bit of a trick, and this has been known since the 1800s, and Lord Rayleigh used this a lot, which is we instead make the source where the listener is, and we solve for the noise close to the edge where the turbulent source was. You can solve that, actually, and then using a theorem, you can actually use that solution to get the inverse, so-called reciprocal solution. It's a pretty neat trick. So deep breath for the next 2 slides. So this is the math model used to the plate. If you get rid of the porosity, which is just these extra terms that involve alpha sub h, then you get your old friend, the beam equation, or the plate equation. And so all these extra terms involving alpha sub h involve the flow going through the pores. And so make a number of assumptions here, small porosity, and that we've essentially averaged out the details of the holes and the plate model. And so you construct this large set of equations. So incident sound field, this matches the fluid velocity of the plate, the velocity of the fluid with the velocity of the plate. This is just the equation for the elastic waves in the plate. This is relating a pressure jump to the velocity potential, and then your Helmholtz equation, which tells you how waves behave as they're scattered from the edge. And you non-dimensionalize, you have 2 parameters here, one's frequency dependent, one's not. And you can solve these using something called the Van Hopf technique, which you'll become aware of if you take 453. So that's the end of that. And what we can get is a scaling for the noise. And this is the main result from the trillion-inch noise work, is that if we look at how the velocity dependence of the noise goes with the frequency of sound, we put the human range of hearing there. For rigid edges, like you have in an ordinary aircraft, this dashed line of the Boeing 777 is frequency independent and goes like velocity to the fifth. That's what we hear. So generally speaking, if you go above the line, it's weaker sound, so it's quieter. And if you go below, it's louder, which actually is kind of a lie, because even though this looks louder, it turns out to be quieter. This is half this load. The point of velocity of 6 and higher is that when you get velocity of 6 or higher, you no longer have the sound being produced as if it's at the edge at all. Velocity of 6 goes like if you had an infinite wall and a noise source above it. So that's a pretty cool thing we found. And if you get something besides, get something above velocity of 6, you have velocity of 7, which is even weaker than no one knew about before. So because we have a model, we could say, well, we could fit it with the elasticity parameters and push this red curve, per se, out of here. So you have this velocity 6 and velocity 7 occurring within the human range of hearing. You've essentially gotten rid of the predominant noise mechanism for trillion edges. So I like to relate it back to the owl. This is actually, I think, is a pretty cool slide, where you have the range of snowy owl down to the northern pygmy, very small owls, and this is a representative range of owl species. And we compared this critical wavelength above which the weather is silent, you get this jump in wavelengths per chord. So when it's above the line, it means they're acoustically non-compact. So what does compact mean? Compact means I can fit a wavelength around the airfoil. And non-compact means I can, well, like this. So the semi-infinite plate model works well there because you don't see the effect of the leading edge in that case. So we know that Harry Potter owl and all the others hunt mice and do quite well. And they're using their acoustic stealth to their benefit, larger owls. The smaller ones, and so this also happens where our model holds. So the acoustically compact wings are on the smaller ones, and those have a completely different foraging behavior. So instead of coasting silently to get their prey, what they're doing is something different. They're sitting up on a branch and they're pouncing down on their prey, or they're hawking things out of the sky. And they're not, so their foraging behavior and the things they're eating, so moths and things like that versus mammals, are linked to the acoustical compactness, which I thought was kind of a neat finding, but it's a hypothesis we're pushing forward. So there's also this bit about the feather I passed around with that kind of canopy layer above. So what we've done is try to make our own artificial canopy, which is just suspending some material you can buy at a department store over a rough surface, and we put a microphone into the wall and measure the noise. So this is to replicate in some sense this kind of fuzzy down material. So that's what it looks like in real life. What does it look like in the model? We have flow blowing over a porous canopy suspended over a rough surface, and we impose some kind of disturbance in the flow and see what happens. So how many of you have heard of something called the Kelvin-Helmholtz instability? How many have heard of shear flow? So shear flow is when you have flow of one velocity, you have flow of another velocity, and it creates a shear between them, right? A different rate. So you have a flow of u here, and of course there's going to be some slower flow here, and this creates a shear at this porous layer. That shear creates a disturbance called a Kelvin-Helmholtz instability. So, and as you go in this direction, you have a growth in the amplitude, exponential growth. But if you go in this direction, normal to that, it's actually exponential decay. So If you have exponential decay over a short range here, then you're killing off the noise before it's scattered. And that's the key ingredient to our model into looking at the porous canopy. So even over 1 millimeter, it's able to exponentially decay large enough to get some noise suppression. So here's what we get from some measurements we took at Virginia Tech. And for different flow speeds, these are noise reductions compared to if there's no canopy at all. So in one case, we get up to 30 decibels reduction in noise. So what does that even sound like? So 10 decibels is effectively half as loud. So this is something that's an eighth as loud under this canopy, which translates to about 5 decibels noise reduction in the far field. So, and also what's kind of cool about this is that you have this finite range frequency that this happens, and the shapes are similar, which suggests that we can construct a model to go with that. And we have. And this is like the ideal result you get as a theorist, right? Because you've shown that you can get the model to work bang on for half of it, and there's still more work to be done, right? Another half. And the second good part about it is that that never happens when you compare theory and experiment, is that the theory underperforms. So the experiment actually is quieter. Positive values are noise reduction. The experiment actually is quieter than our theory predicts. So that's good news for us. It pushes us to kind of revise this theory to get the high frequency noise attenuation. So where does this all fit in? Small scale flies, micro air vehicles are things you'd like to have be stealthy or about the size of owls. We can have more of a direct application. We've had a lot of interest actually from the wind turbine industry. We have 2 patents pending with some noise reduction technology to go on those, and we're pretty excited about that. And lastly, underwater vehicles, some of this is supported by ONR, and if you have something that can reduce the noise of a submarine or the rotors, our model, all we do is change a parameter or two, and it goes from being in air to being in water. And that's the power of having a theoretical model to do all of that. So there are, of course, opportunities for motivated students to look at these things. So I work mostly on the mathematical modeling side of it, aerodynamics, aeroacoustics. There's even some field work that is possible. Reconciling zoological data with measurements of these feathers as an engineer would look at them. So as well as look at the feather you gave him that is passed around and says, well, I measured these things. But aerodynamicist looks at it completely differently. And that's something that has to be fixed. And there's a number of collaborators I have ongoing in different countries, the UK, Brazil, Germany, Australia, that are keen on working on this together. So if you'd like to know more, there's some reading. This is a journal paper and a conference paper. I had a nice nod. I'm very happy to have the acknowledgement of some popular media. So given that Rose Constance of the Skies covered some work on the trailing edge noise, as well as pop mechanics and as well. So with that, a small commercial to thank the libraries, as well as these folks that I've worked with, as well as the postdoc at Cambridge, and my collaborators have developed a relationship with since then. So thanks very much for listening.